Hey guys, so this is me editing from the future with a couple of helpers here at home. Just a couple of things for this video. So I just had a student help me record the lecture today in class. You'll see a lot of jump cuts. It's just to keep out awkward silences, or if we got off on a tangent that wasn't important, or I can't post things online that have pictures of other people or video, and so if the camera moved and showed a student, I did have to cut that out as well. So that just kind of explains your jump cuts. If you have any questions or issues with this assignment, feel free to shoot me an email and I'll help you out.
You guys remember, I mentioned to you that there are 9 different types of energy, but there are 2 categories. Okay, we've not gone over all 9 types, but we have talked about the 2 categories. So let's review a little bit. What are the 2 categories of energy? Remember, Paige. Okay, potential is one of the categories. Okay, what is the other category? So we had potential, and the other? And kinetic from the birthday boy. Okay, now we've talked about a couple of the different types of energy that are found in these 2 categories. Like we mentioned, mechanical energy is motion in the kinetic category. And then yesterday we talked about gravitational energy as a type of potential energy. Okay, but today we actually want to talk about another type of potential energy called elastic energy. Okay, elastic energy. And so what we're going to do first is we're going to do a series of different things, and we need to determine and categorize into the assignment, into the slide, whether each of these things demonstrates elastic energy or gravitational energy. Okay, does that make sense? So let's go through this here. What's the source of energy here? Is it elastic or is it gravitational? Okay, so let's give it a shot here. My balloons having issues. There we go. There you go. That's as much as you're going to hear. So, was that elastic or gravitational? Let's give you a second. Hurry and fill that in the slide, and then we'll discuss it. Okay? So, how many of you think that's gravitational? Raise your hand. Nobody. How many of you think it's elastic? All right, so everybody's thinking that's elastic energy. We're not quite sure what elastic energy is, but we know it's not gravitational, right? Okay, so let's try another one. Well, I've got the balloon here. Okay, this is another one everyone's done, where you fill up a balloon and then you just let go and let it do its thing. Okay? So, once again, you're just considering, is this elastic or gravitational? Here we go. That was really cool. Okay, thanks. Okay, so the flying balloon. Is a flying balloon elastic or gravitational? Okay, how many of you thought it was elastic? How many of you think it's gravitational? So gravitational, we learned yesterday, we talked about how we pick something up, it gains gravitational energy, and then we drop it, and it loses that gravitational energy. But just barely, I just picked up and dropped the balloon, and when I let go of the balloon, that's not how it behaved, right? It like spun around and flew around the room. So why then? Why did it do that if it has gravitational energy? Because that doesn't follow what we were studying yesterday. It has elastic energy, but it fell. Yeah.
It was releasing its energy.
That's true. It's releasing its energy as it falls as well. Any other thoughts? Yeah.
Both.
Both. Is it possible to have 2 energies existing at the same time? Okay, maybe it is. But we need to consider what makes them separate from one another and keep that in mind. Okay? Well, talking about things falling, let's do this here. So here I have my handy dandy stick. So if I take this and I drop it, is that gravitational or elastic? Gravitational. You guys seem pretty confident, so go ahead and fill that in. Okay, so right here, I have what's called a Newton's cradle. Okay? So this is a Newton's cradle. I don't know if you guys have seen this before. But what you do is you've got normally more than 4 steel balls, but this one's broken. You take one of the balls and you pull it up, let go, and it oscillates back and forth. One thing that makes Newton's cradles really cool is that they conserve a lot of energy. And so it can actually sit here and oscillate back and forth like this for a long time before it actually expends all its energy. Okay? But what we need to be considering is what kind of energy is it expending? Is this elastic or is it gravitational?
Elastic.
What makes this similar to a balloon? If it's elastic, what does it have in common with the balloon?
Like the balloon didn't fall immediately, and this isn't running out of energy.
I kind of see what you mean. Though I don't know if it's exactly the same in that regard. Okay, let me show you some other cool things you can do with this. I can take one from each side, like that. Okay. Think about this. Think about what do I do to initiate this? What did I do to initiate the balloon? I blew up the balloon. I inflated it, right? What am I doing to initiate this reaction? I'm lifting it up. So does that make it elastic or gravitational? Luke?
Gravitational. Elastic. Yeah. Yeah. No. I don't know.
Okay. Show you one more. This one's probably one of the coolest. Look at this. Okay. Can you guys see from over there? I'll try and move it so you guys can see here. Okay. So how did I give the stick gravitational energy? What did I do? No, not dropping it. I lifted it up. Okay, I lifted it up. Okay, how did I give the balloon elastic energy? I blew it up. I inflated it. Okay, so what did I do here? I lifted it up. So that would argue that this is gravitational. Okay? Okay, let's do another one. So I've got a rubber band and a piece of paper. Okay, hold that like this. Take my paper. Why? Why does it represent elastic? I didn't inflate this.
Because it is elastic.
It's a rubber band. Some people call them elastics, sure. But
Stretch.
because it's stretchy. Okay, now balloon is stretchy, that might fit. Might fit. Okay, so we're thinking elastic. Well, what if I go like this and I just wrap it around on my finger? Okay, and I shoot it into the room. Okay, was that elastic or gravitational?
Elastic.
Are you guys recording all these still? Okay, so we're thinking it's elastic.
Yeah.
Okay. So how many of you think shooting the rubber band is elastic? How many of you think it's gravitational? Okay. Okay, let's do another one here. I think we're starting to get the picture here. Okay, so this is my little makeshift pendulum, okay? Pendulums are really interesting. You lift them up and they swing back and forth. And one thing that makes pendulums kind of fun is that you can actually set up a pendulum. A pendulum, you start it at this point, it'll swing, it won't come back to that point because it lost some energy. Not all energy is retained. So one thing I'd always wanted to do is build a pendulum with a bowling ball and set it up like facing a kid's face. Let it go and have that bowling ball come flying back at their face, knowing that it's not going to hit them.
What if it does? Or what if it does?
That's the
a
fear.
lawsuit.
That's the fear that a student would have. What if this does hit me? Huh? Oh, you'll be my test subject. I have the bowling ball, but I've never made it into a pendulum because I don't have anywhere to hang it from. Pendulum. Pendulum, is that gravitational or elastic? Gravitational? Ooh, we've got different thoughts.
It's gravitation because you haven't pulled up.
I had to lift it up, so you're saying it's gravitational?
On all the ones we've said elastic, you're just giving them energy and then releasing them kind of instantly. It's the same thing with that.
No,
Like,
that one's like a Newton's cradle though. What if it's both?
What if what?
What if it's both?
What if something's both?
Yeah.
That's an option, but this one is not both. Okay? Let's look at our last one, a tennis ball. So I'm gonna take a tennis ball, I'll lift it up, drop it, catch it. Are you sure?
Yes.
Then how did I catch it?
Because you have your energy.
The stick didn't bounce up. I didn't catch the stick.
It's because you dropped it a different way, and that has more.
Different material, that's true.
Still have the energy from what it did.
I like that we're thinking.
That's hollow.
It is hollow, that's true. Okay? Yeah?
It's rubber inside.
Elastic.
Have you guys ever seen what a ball looks like when it bounces, like as it hits the ground?
No.
They'll compress, right? They'll change shape a little bit, and then they shoot back to their old shape as they bounce back up, right? That happens to a tennis ball. Okay, so it's able to absorb the impact, but then what energy does that become as it absorbs it? Because it's not gravitational, but it's changing shape.
It's elastic.
You're thinking it's elastic, but I dropped it.
Yeah, but it came back up.
But it came back up, but I dropped it.
It went from gravitational to elastic.
So you're saying it's both,
So
that it was gravitational, elastic, and
But
back,
not, yes, but not at the same time.
but not at the same time. These are both, but not at the same time.
I have
Okay.
a question though, because
Yeah.
in the Newton's cradle, then you didn't lift up the other side, you lifted up this one and gave that one. So is that,
So that it is technically different, but I'll explain why after we come up with our definitions. Does that make sense? If I explain now without your definitions, then I'll be telling you how to define them. Okay, based off of the definition of these two terms, they are different. Okay? All right, so we fit this under both, right? Not at the same time, but they are both. Okay, right? Okay, so let's go through then and let's decide how we want to define gravitational and elastic energy. Okay? How would you guys define gravitational energy? And let me ask this differently. What did I need to do each time in order for an object to have gravitational energy? I had to lift it up, which then, to demonstrate that it had gravitational energy, I dropped it, right? I let go. So, I would say that gravitational energy is an object, or is the potential of an object to what? The potential of an object to what? To fall. The potential of an object to fall. The higher we lift the object, the more gravitational energy it has, and therefore the farther it can fall. I like that. Does that sound good to you guys? Okay? Gravitational energy is the potential of an object to fall. Okay, what about elastic energy then? I want to use similar terms, so I'm going to say the potential of an object to what?
like, it's like the opposite,
To float?
like, no, like. You know,
Think about what happens to the rubber band, the balloon, and the ball when it hits the ground.
Potential of the object to bounce.
It's not bounce, but you're getting there.
They all change though, like. they're
What
not-
changes about them?
Shape.
They all change shape. But Play-Doh changes shape. We wouldn't say it has elastic energy.
Because it doesn't come back to its original shape.
That's the key, right? It's the potential of an object to what?
Come back to-
Go back to its original shape. Potential of an object to return to its original shape. Okay, I like it. So, to answer your question earlier, what makes this different is the tennis ball changes shape as it hits the ground, where this never changes shape. Instead, the energy travels through the others, moving this up, which then is gravitational energy on this side, which travels through the others, moving this up, which is gravitational energy on that side. So this is just going from gravitational to mechanical to gravitational to mechanical to gravitational and back and forth without any change in shape. Okay? All right. So what we want to do then today is we want to test you guys' hypothesis, or your definition. Okay? So on slide 2, I've given you a testable question that says something along the lines of like, what's the relationship between how far we stretch a rubber band and how much energy, elastic energy, that rubber band has? Okay? I ask you that question. Let's give you guys a second here to fill out your hypothesis. Okay? What do you think will happen? What's the relationship? As I stretch out the rubber band, what happens to the energy? Okay. So you're saying the more it's stretched, the farther it fly, the more energy it has? Okay. So you guys are saying the more we stretch out the rubber band, the more energy that rubber band has, right? Anyone say anything different than that, or did you just say the same thing in different ways? Okay, so how could we test that then? How could we test and find out if that's true? The more we stretch the rubber band, the more the rubber band has different amounts of energy. Yeah.
With that paper and launch it from different distances.
So stretch it out different distances,
Yes, and then shoot the paper.
and then shoot the paper, or what about just shooting the rubber band?
Oh,
How far it goes.
Okay, either one, shoot the rubber band even. So if we say our experiment is to stretch out the rubber band, launch it and see how far the rubber band goes, what's our independent variable?
the distance you shoot.
How far we stretch the rubber band. Okay, what's our dependent variable? How far the rubber band goes. Okay, so what would be some variables that would need to stay the same? Would be controlled variables. Need to use the same rubber band. Good. What else?
What you measure.
How you measure. Okay, it needs to be the same. What else? If I want a rubber band to fly really far, what am I going to do? Yeah, the angle I shoot at is going to be different, right? So you need to have a consistent angle. Yeah. Okay. Okay, weather conditions, wind, temperature, things like that. Okay. What about the height? If I shoot from like 6 feet or 6 inches off the ground versus 6 feet off the ground, is that going to be different? Yeah, so the height that the rubber band is shot from needs to stay consistent as well. Okay? So, what materials would we need to do this? How would we measure how far we stretch back the rubber band? A yardstick, but this doesn't stretch a full yard. We might not need a full yardstick. A ruler, okay, we could use a ruler, and then how would we measure how far it went? Then we could use yardsticks. Okay, so let's kind of consider this. So I've got a ruler right here, okay? Now, a ruler, we measure in centimeters or inches? Centimeters, okay? And a ruler has a little over 30 centimeters, and let's say we wanted to run 3 trials. What distances should we stretch it back to?
10, 20, and 30.
10, 20, 30? Okay, we could do that. So let's just say I did one at 30 here. Oh, sorry, Gunner. Okay, but that's a long ways over. That's a long ways down, right? And that'd be a lot of yardsticks, a lot of meter sticks, right? So like a tape measure might be better, but we don't have a tape measure here. So
Eyeball.
Yeah, when he did what? 6 or something. Yeah, like.
you could do that, but if you don't stretch it out at all, then it just falls. You know what I mean? What you could do instead, though, is have you ever like measured how big something is by steps and just said it's this many steps long or whatever? As long as you have a consistent step, then that could work, right? I could be like it's 1, 2. Is your step going to be the same as the other people in your group?
No.
No, some people have long legs, some people have short legs. So that'd be different. So whoever measures steps needs to be one of your controls, right? They need to measure the steps each time. Does that make sense? Okay. So why don't we do this then? How many trials would we want to run? 3 and do like an average?
Yes.
Okay. So if you look, we need to fill out materials. What materials did we need?
Rubber band.
Rubber band and a ruler. Okay, and feet. You want to list that? Okay, and then steps.
Someone to shoot.
Okay, need someone to shoot it, right? On procedure, we'd need to stretch out the rubber band, launch it, walk out to see how far it went, rinse and repeat, right? Okay. Then, how many of you guys noticed on slide 3 that I've already set up a data table for you
You plan
for
this.
3 trials at 10, 20, and 30 centimeters, right? Okay, so we're gonna do this, okay? You can spread out in here and in the lab, okay? However you need so that you have enough space, okay? Working with your lab group. As soon as I give you your ruler and your rubber band, go ahead and get started.